In this session, we will see about the various interaction between radiations and matter. As you may already know, radiations can constitute charged or unchanged particle. Uncharged particles can be gamma or neutron particles. But all the interaction involve charged particle at one stage or the other. Especially in the case of gamma, neutron particle, they transfer energy to charged particle before getting absorbed in the medium. Now we will take about each case separately. Consider the interaction of charged radiation with matter. As radiation constituting passes through matter, they interact with atom. As they interact, they lose its energy due to its action of its F on atom. Most of energy carried by electron than heavy nucleus. However, in the case of interacting particle carrying high energy, ions also have effect on energy loss. Next we will take a look at how the gamma ray or X-ray interact with matter. This is possible in three ways: photoelectric effect, Compton effect and pair production. All are familiar to us. Now we will just skim through those points we already know. Suppose consider the radiation carrying packet of energy called photon, is incident on the matter. Matter consists of atom with positive nucleus and orbiting electron, and may be free electron. Now if the incoming photon is incident on atom, transferring its all energy to orbital electron, knocking it out of atom. And these electrons are photoelectron and phenomenon called photoelectric effect. For this to happen, incident photon must carry a minimum energy called threshold energy, which depend on the material. Other possible interaction of incoming radiation is with free electron. As you may see in the second figure, the incident photon strike on free electron. After collision, photon emerges with lower energy, electron recoil with kinetic energy depending upon scattering angle. Thus the incident and emergent radiation will different energy, thus different wavelength. This is called Compton effect. Another possible interaction is just conversion of photon energy into creation of electron-positron pair in presence of atom. The graph indicate which among the three process is most probable at particular energy range. At low photon energies, the photoelectric effect is the chief mechanism of energy loss. The importance of the photoelectric effect decreases with increasing energy. In the lighter elements, Compton scattering becomes dominant at photon energies of a few tens of kilo-electron-volt, whereas in the heavier ones this does not happen until photon energies of nearly 1 mega-electron-volt are reached. Pair production becomes increasingly likely the more the photon energy exceeds the threshold of 1.02 mega-electron-volt. The graph of the linear attenuation coefficient for photons in lead as a function of photon energy is given. And what about neutron? How do they interact with matter? Interaction of neutron with matter is mainly by nuclear reaction, which depend on energy of incoming neutron and nuclei on which the particle collide. This is predominant interaction. Neutron scattering is the other possible. In this case it is the recoiling nuclei that takes most of the energy. As now we have a general idea about how the radiations interact with matter, we will move to our main topic, which is detector. We casually say that some radiations or particles were detected. But how? We often don't care. But as physics students, aren't you curious what's happening inside? And how do we detect and recognize the particles, but just getting some parameters and image? So we will get to know more about what are the devices that we use for detecting particles, their working and how we conclude the nature of particle. So we will start from nuclear detector. As the name indicate, nuclear detector is the device used to detect, track, and or identify ionizing particles, such as those produced by nuclear decay, cosmic radiation, or reactions in a particle accelerator. In simple words, these are the devices used to detect the particles. Ionization chamber, proportional counter, Geiger-Müller counters and semiconductor detectors are based on detection of free charge carriers, whereas scintillation counter and Cherenkov detector are based on methods of light sensing. We also have Wilson cloud chamber, bubble chamber, nuclear emulsion plate, spark chamber and solid track detector, that working principle based on visualization of tracks of radiation. It might sound hard to understand. Don't worry, we will see each of them in detail. I want to discuss the general principle and working mechanism of gas-filled detectors, which include ionization chamber, proportional counter and Geiger-Müller counter. We will see their construction and working in detail. Let's take a look at the general construction of ionization chamber. So while we have a conducting hollow cylinder filled with hydrogen gas at 1 atm pressure and a metal rod held axial to cylinder with help of an insulator so that there is no direct contact with metal rod and cylinder. The cylinder is connected with negative terminal of the battery while metal rod connected to positive terminal through resistance R. An amplifier or a pulse counter that can basically detect the potential drop that is happening across RL and measure the amount of current, which is passing through R. Whenever energetic radiations, say alpha, beta, gamma etc., they may collide with atoms or molecules transferring a part of its energy to them. If the energy of incoming particle is sufficient enough, they might knock out electron in orbit of colliding atom out, thus producing free electrons and positive ions. This ionization is primary ionization. And the ions created initially are primary ions. These primary ions will move towards positive and negative electrodes in detector. That is, the free electron will move towards positive electrode while holes move towards negative electrode, resulting in ionization current through external circuit which is recorded using suitable device. Now if potential difference between electrode is high enough, primary ions may gain energy to collide with other atoms in its way towards electrode producing more No. of ion pair. These ions are secondary ions that might add up to primary ions, amplifying current T in the detector. This process is gas amplification. When radiation fall on gas medium in cylinder, electron-hole pair produced due to primary ionization. Electron move towards metal rod and hole towards cylinder respectively. Electrons may move through outer circuit resulting in ionization circuit and voltage is dropped across resistance which is measured by amplifier and pulse counter. Here the magnitude of current detected depends on two parameters, the energy of incident radiation and the magnitude of voltage applied. More energy of incident radiation, more will be the number of collision, more number of electron-hole pair produced and more will be the ionization current detected. And what happens when we increase the voltage of battery connected? Let's see it in detail. To understand how the magnitude of the current pulse change with energy of the incident radiation and applied voltage, just look at the graph plotted taking the magnitude of voltage along x-axis and log of pulse size along y-axis. The red and blue curve is for beta and alpha particle respectively. Graph here at very low voltage, electric field build-up across metal rod and cylinder is not strong enough to accelerate the electron-hole pair towards electrode and hence they might recombine, hence do not contribute much to current. As voltage increases, electric field becomes stronger and the rate of recombination become less and less resulting in increases of current. At some particular voltage, recombination become almost impossible that all the primary ions results in current through the circuit. After this point, even if we increase the voltage, current will not increase but stays constant maximum value. This region is ion chamber region in which current pulse remains same magnitude even if we increase voltage. In this region we can distinguish the incident particle by magnitude of current. More the energy of the incident particle, larger will be the magnitude of current pulse. That is, the detector working in this region, we can say which particle is having higher kinetic energy by looking at the current pulse. Now what if we increase voltage beyond that value? If we further increase the voltage, the strength of electric field increases, the primary ions may gain more kinetic energy and collide with more molecules causing secondary ionization. There is a cumulative addition to the total number of positive ions and electrons due to secondary ionizations. So as we increase the voltage further, the energy of the electrons and the ions becomes so high that they themselves cause secondary ionization, thus increasing the total number of ions and leading to an increase in the current pulse. In this region, it is seen that as voltage increase, current increase linearly represented by a proportional curve. If suppose the incident particle have low energy which is insufficient to induce ionization, current pulse would be so small that it would be difficult to differentiate them from noise. In such case, to distinguish pulse from noise, it's better to increase the current pulse by increasing voltage. In this region also we can distinguish incident particle comparing magnitude of the current pulse. A detector which works in this region is proportionality counter which can be used to detect less energy particle. Now, if we further increase the voltage, this leads to sort of an avalanche effect in which the primary ion will create for the secondary ions will create for the tertiary ions. This avalanche effect will increase the total number of ionizations, that we will end up going to a region where there is a limited current. the applied voltage applied is in the range 1000 to 3000 volts. When an ionizing particle enters the counter, ionization takes place and a few ions are produced. Since the applied voltage is high, the electric field accelerating ions will be high. This increases the rate of collision, thus ions are multiplied by. Thus an avalanche of electrons moves towards the central wire, and this is equivalent to a small current impulse which flows through the resistance. And now if we suddenly lowers the critical potential, a sudden discharge through the resistance R. The potential difference that is devolved across R is amplified by vacuum tube circuits and is made to operate a mechanical counter. In this way single particles can be registered. The sudden pulse of discharge sweeps away the ions from the chamber and the counter is ready to register the arrival of the next particle. Now take a look at the Geiger region of the counter. There is a threshold below which the tube does not work. This can be several hundred volts. As the applied potential is increased, the counting begins and rises rapidly to a flat portion of the curve. That indicate count rate is more or less independent of applied voltage is called the plateau. In this region we can only get idea about arrival of ionizing particle, not its nature or energy. This is one of the disadvantage of Geiger-Müller counter. Counting efficiency may be defined as the ratio of the observed counts per second to the number of ionizing particles entering the counter per second. This indicates ability of its counting, if at least one ion pair is produced in it. Counting efficiency equals 1, e raised to SL, where S is specific ionization at 1 atmosphere, P the pressure in atmospheres and L the path length of the ionization particle in the counter. Look at the graph which shows efficiency as a function pressure for both hydrogen and air. It's seen that initially with increase in pressure, efficiency is slowly increasing and beyond a certain pressure, efficiency almost remain constant. Geiger-Müller counter has many advantages. The first advantage is that this type of counter is portable and serves best for mineral prospecting, apart from its several other applications in cosmic ray work. As we already know from the voltage characteristics that, the pulse height remains constant over a range of voltage mainly 1000 to 3000 voltage which we call plateau region. So in this region, small changes in power supply does not have much effect on reading, and this is contrary to proportional counter in which voltage have a proportional effect. Hence in Geiger-Müller counter, we don't need a regulated power supply. Also, the pulses are several volts in height, which makes amplifiers unnecessary. All these are advantages of GM counter over the other counters we discussed so far. But in those detector, we were able to identify by comparing pulse height. But in GM counter this is not possible. So GM counter cannot provide information about the particle or photon causing a pulse. Also it is insensitive for a period of 200 to 400 microseconds following each pulse, which prevents its use at very high counting rates. Now let's see about construction and working of an instrument used for obtaining track of charged particle moving through the matter. Well, one of such instrument is Wilson's cloud chamber, which was designed by Center Wilson. The basic construction is shown in the figure. The apparatus has a mixture of dust-free air with water vapor or some other volatile liquid like alcohol contained in a chamber with glass wall and ceiling. The chamber has a movable piston P, as you can see in the bottom part of chamber, which can be pushed in or pulled out that we result in adiabatic compression or expansion. A camera is placed on the top of the chamber to capture photograph of the track of charged particle. To avoid unnecessary reflection of light, the piston surface is covered by black felt. As now we know the construction, but what is the basic principle behind this? Let's see what it is. Consider a mixture of air and saturated vapor. If suddenly this mixture is adiabatically expanded, temperature falls and it results in supersaturation of vapor. The vapor now will condense in cloud of water droplets. Here it's the dust particle that act as condensation nuclei. But what about mixture in Wilson's chamber? We already specified it's dust-free air. Then how will condensation occur? Wilson discovered that it's possible, if we ionize the air particle by agents such as X-ray, cathode ray or other radiations. These ionized particle now will act as condensation nuclei. As supersaturation increases, negative ions first, and as volume increase, both positive and negative ions may act as center of condensation. Hence the track of the particle becomes visible. This will be more clear once you see the working. Let's see the working. At first alcohol is sprayed into the dust-free air and the glass window is closed. Alcohol will begin to vaporize in air. The piston is suddenly pulled out. Since it's an adiabatic process, temperature falls. So alcohol will vaporizes on air. And this is supersaturation state, shown in figure 3. Now the ionizing beam, alpha, beta or any other energetic particle whose track needed to be studied is allowed to pass through the mixture. They ionize the particles on mixture. The alcohol will condense on these ions, which now will act as ionization center. Due to condensation, these droplets appears like cloud. So we see cloud in the track of ionizing radiation. Now, the photograph of this cloud is taken with help of camera. If cloudy path is thick straight in photograph, it will correspond to alpha radiation. And if track is discontinuous and thin, it will correspond to beta particle. And if there is no track, it correspond to gamma rays. If we want to reuse the chamber, we can apply 1 kV potential difference using battery, and thus unwanted ions are cleared and become ready for receiving next radiations. For now, we know the basic construction and working. Now let's see the advantages and disadvantages of this method. By using cloud chamber we can study the variation of specific ionization along the track of a charged particle and the range of such particles. If we apply a strong magnetic field to the cloud chamber, the ionizing radiation follows a curve of radius r. We know if a charged particle undergoes such curved motion, magnetic force and centrifugal force balance. That is BQV equals mv square by r. So by rearranging equation we get momentum as BRQ. Here the symbols B, Q, V, M represent magnetic flux, charge, velocity and mass of moving particle. Also, if we know rest mass energy we can determine kinetic energy of the particle. But using cloud chamber we can determine charge and momentum of particle. Even though W have advantage, we have few disadvantages. One is not always sure of the sense of track photographed. Let's say, the ionizing radiation have range, more that dimension of cloud chamber, then properties determination poses struggle. Also, there remains a certain amount of uncertainty about the nature of the nuclei constituting the arms of the forked tracks. We cannot continuously record the track since needs a cover time from adiabatic expansion. Interaction of highly energetic particles cannot be completely observed and studied using Wilson's chamber. So how do we detect high-energy particles? Yes, for this purpose we use yet another particle detector called bubble chamber, discovered by D. Glaser at University of Michigan in the year of 1952. So let's see the working of bubble principle. By the way, why there is term bubble? Just recall that in Wilson's cloud chamber we discussed the case of supersaturation. Here, we will discuss about superheated state. We know normally when a boils at boiling point, there is formation of bubbles. Now, if the liquid is heated at high pressure, boiling point is raised above normal boiling point without boiling takes place. Now if the pressure is suddenly released, this would leave liquid in superheated state, that is liquid remains without boiling for some time. If we allowing ionizing radiation to pass through a medium that is in this superheated state, ions in the traco radiation act as ionization center for formation of bubbles. Thus an ionizing particle passing through the superheated liquid leaves in its wake a trail of bubbles which can be photographed. Since its trail of bubbles tracked, the name of detector. So, this is the basic working principle of bubble chamber. The construction of bubble chamber is shown in the diagram. Take a look at it. We have a cylindrical chamber kept between optically planed glasses containing liquid. Fitted with the cylinder we have bellows and expansion piston, which helps to superheat the liquid. The setup as whole is places in temperature control system like shields of liquid nitrogen and liquid hydrogen. As you may see, the flashlight enters the cylinder through bottom, and camera is placed on top capture track of bubble formed. As you may see, there is also electromagnet on either side of chamber. This set you is to study the charge mad momentum of particle as earlier. Now let's see the working. The liquid is first heated to a temperature above its boiling point. By applying a pressure greater than saturation pressure, it's kept in liquid state itself. Now, the pressure is suddenly released. This would leave liquid in supersaturated state. Just before pressure falls to minimum, flash lamp is switched on. For milliseconds of times, bubbles grows and the centers for bubble remains for this time. This tracks is photographed using camera. This process can be repeated. The charge of the tracks can be identified by the direction of their curvature in the magnetic field applied over the bubble chamber. From the curvature and length of the track, the momentum and energy of the particle can be found. Using bubble chamber, one can study particle interaction and to detect very high energy particles. Momentum and energy of the particle can be found. Apart from this, there is a greater chance of their track being recorded owing to high density and chances of collision with ionizing particles. So the chances of recording events like cosmic ray phenomena are improved when compared with cloud chambers. The bubbles grow rapidly, and as a result the tracks are not likely to get distorted due to convection currents in the liquid. And the bubble chamber is sensitive even to particles of low ionizing power. However, there is difficulty with the low boiling point. For an example, in case of hydrogen chamber must be operated at 26 K. Now we will discuss yet another type of detector called semiconductor detector that make use of semiconducting crystal sandwiched between two conducting electrode. Across the electrode we have applied an electric field. As next step, if nuclear radiations is passed through them, an electron-hole pair is produces which move towards appropriate electrode. This charge is collected is used as the signal for studying radiation. We have two types of semiconductor detectors, diffusion junction detector and surface barrier detector. These type of radiation detector is important in comparison with other type of detectors since it has with better resolution, linear response over wide range of energies of incident radiation and fast response. So we will see each semiconductor separately. This detector consists of a PN junction which is reverse biased. That is P connected to negative terminal of battery and N connected to positive terminal of battery. As result, electrons and holes drawn apart from the depletion layer with no charge carriers. So diode is O-off state and no current flows. As you might already know that thickness of depletion layer depend on the nature of impurities and applied voltage. So, a large potential difference is maintained across the depletion layer which has low conductivity. This setup acts as an ionization chamber. Now if high energy particle passes trough the depletion layer, electron-hole pair would be produced. Electron move to conduction band, while holes moves to valence band. So, a momentarily current produces, whose magnitude proportional to number of electron-hole generated. So, diffusion junction detector act as solid-state ionization chamber. If diffusion junction detector act like a solid-state ionization chamber, what is its difference or advantages over ionization chamber? Energy needed for production of electron-hole pair in ionization chamber is 30 electron volt, which is much greater than energy needed for the same in semiconductor detector, which is only 3 electron volt. Registration of electronic pulses in semiconductor detector is more easier and energy measurement are accurate up to fraction of percentage. But as more narrower the depletion layer gets, pulse rise time becomes low. In solid-state detectors for charged particles, silicon has been used most because of its low intrinsic conductivity. This means that the detector can be operated at room temperature without excessive leakage current. For gamma-ray work, germanium detectors are much better than silicon because of the larger density of germanium. Next type of detector is surface barrier detector. The diagram of one of them made up of silicon is shown. As for the structural construction, it consists of a thin p-type produced on high purity n-type silicon. For this take n-type silicon wafer, etch one surface with acid. An oxidation layer is formed on this etched part if we expose this portion to the air. Electric contacts are provided by evaporating gold on p side and aluminium on n side. Under influence of externally applied field, electron move right and hole left and depletion layer is formed. On passage of radiation, electron hole produced and that will swept towards appropriate electrode. This result in a current pulse. These type of detectors have advantage of long stability, small size, negligible window size and linear response over wide range. Next type of detector is named as scintillation counter, which is one of the earliest form of detector, even used by Rutherford and his colleague. Before going into that we need to know about the terms scintillator and scintillation. Scintillators are nothing but phosphor substances that emit light flashes when charged particles like X-rays or gamma rays falls on them. And this, momentary flashes of light are called scintillation. Few examples for them are ZNS activated by silver, Ni activated with thallium. One of the earliest methods of radiation detection was the spinthariscope that consists of a small wire, the tip of which is dipped in radium bromide or any other radioactive salt, which is placed in front of a zinc sulfide screen S and viewed through a microscope. When an alpha or beta particle falls on the zinc sulfide screen, they produce light flashes which can be seen by a microscope in a dark room. The visible luminescence excited in zinc sulfide by alpha particles was used by Rutherford for counting the particles. The process of counting these scintillations using a low-power microscope is tedious, and the eye restrict the counting rate to about 100 per minute. This process, whereby the energy of the particle is converted to light, is the basis of scintillation counter. Now we know the basic principle behind scintillation counter. Now let's see what are the main parts of a scintillation counter. When radiation incident on phosphor atoms, they receive energy and goes to excited state. Since excited state is not stable, they return to ground state emitting extra energy in form of photons in the blue and ultraviolet regions of the optical spectrum. The phosphor is optically coupled to the envelope of a photomultiplier tube. The photons strike the photocathode, causing the ejection of photoelectrons. As these photoelectrons leave the photocathode, they are directed by a focusing electrode to the first multiplier electrode or dynode. This electrode has the property of emitting 3, 4 or 5 electrons for every single electron which strikes its surface. There may be from 10 to 14 such multiplier stages in a given tube. Hence, from the emission of one single electron from the cathode, a burst of 1 million electrons may impinge on the final stage in the tube. The output pulse from the photomultiplier is fed to a pulse amplifier followed by a scalar circuit. Output will be proportional to energy of incident particle on phosphor. Scintillation counter have wide range of applications, like they are used to measure particle energy, detect antiprotons, mesons and other unstable particle at high energy, in study of cosmic rays, and due to rapid response used for accurate timing of nuclear particle moving with very high speed. All these applications are possible because they have greater stability, accuracy, high efficiency than GM counters, shorter resolving time, and high counting rate for gamma rays, since they dissipate more energy. So, in this section we discussed about various particle interactions and different types of detectors, their working, merits and their demerits. In next session we will see a set of instruments that can accelerate particles, generally known as particle accelerators. So see you in next session. Till then, bye.